input intelligence on mobile devices. Over the past decade, the confluence of sophisticated algorithms and tools, computational infrastructure, and data science has fueled a machine learning revolution across multiple fields, including speech and handwriting recognition, natural language processing, computer vision, social network filtering, and machine translation, etc. So ensuing advances are changing the way we interact with the technology in our daily lives. So our speaker, Dr. Jerome Bellagada, he is going to brief about the input intelligence and mobile devices. It is my pleasure to introduce today's speaker, Dr. Jerome, who is working as a Apple Distinguished Scientist in Intelligent System Experience, Apple Inc., Cupertino, California. I welcome you, sir.
Very much, Dr. Nagamani, for this kind introduction. So yes, indeed, I'm going to talk about input intelligence on mobile devices. You will find this talk maybe a little unusual for, it's not going to be the same as a typical IEEE Signal Processing Society talk, in that it involves not just the processing of, say, an acoustic signal or an imaging signal or radar signal, but actually the processing of multiple signals taken in the sort of more general sense, multiple signals that can happen on device. So the concept we're after is input intelligence as it pertains to mobile devices. And by design, I'm going to go broad rather than deep to cover a wide range of things that have been done in this area over the past few years. What I hope to achieve is illustrate the many ways in which signal intelligence, in the most inclusive sense of the term, can improve user experience, the experience that the user feel when they use their device. One caveat before we start, since I'm from Apple, inevitably everything I'm going to say is going to feel very Apple-centric. But I want to point out that a lot of the features that we'll talk about in the next few minutes are available not just on Apple platforms, but on other platforms as well. Okay, so what exactly is input intelligence? Intuitively, it has something to do with entering data into a device. But more specifically here, the goal is to improve interaction experience through data-driven processing, or actually, as it is known these days, machine learning. Data-driven processing it feels a bit like last century. Now everybody talks about machine learning, but it's really the same idea. Okay, so now what is indeed, or what do we refer to by interaction experience? We're really talking about any form of interaction between a human and device, including so the direct interaction between human and device, but also between human and cloud, perhaps through the device, between humans as mediated by a device, and so on. And this talk we will focus on direct human-device interaction, as this picture shows here, when a person either speaks or writes or types, or perhaps take a picture using a device. Now, what do we mean by device? We might be talking about a laptop, a tablet, a phone, a watch, a smart speaker, a TV box, and so on and so forth. The list seems to increase every single day. And those devices offer multiple data entry options, such as a hard keyboard, a soft keyboard, a trackpad, finger and stylus, microphone, camera, remote control, and so on. So the combinatorics of the interaction space quickly become overwhelming. In addition, there is an extra level of difficulty because this interaction between human and device involves creating and manipulating user data, whether it's speech, text, handwriting, or photos. That's our personal data that is being dealt with here, which means that we've got to talk about privacy. Over the recent past, we've all come to realize that our data can sometimes be exploited in all sorts of creative ways, and often without our knowledge, which eventually led to legal frameworks like the GDPR in Europe, now being more or less adopted all around the world. For example, California has a very similar sort of set of regulations. Even China has also some GDPR-like rules to comply with. And this reflection around data privacy and data security has actually introduced some useful concepts like transparency, consent minimization, and so on. But beyond the legal aspects, even more importantly, respecting privacy gives the user cognitive sovereignty over his or her own data. And that in turn gains user trust and thereby promotes user engagement with the particular feature that are the feature or features that are being deployed, which is, of course, exactly what we want. We want users to engage with our features. But in addition, beyond the legal aspects, besides the desire to increase engagement, at the end of the day, respecting user privacy is simply the right thing to do, which has always been our position at Apple. Our core belief is that privacy is a fundamental human right, and that safeguarding the user data entrusted to us is inherently a moral imperative, as nicely expressed in this quote from Apple CEO Tim Cook. So, what's the absolute best way to keep the data private? Well, it's to make sure that it never leaves the device in the first place. If the data stays on device, then the only way it can be accessed if the device itself is breached, which is another story, which we're not going to get into here. But at least there is no way that it can be observed while in transit or on a server or whatnot. So for this reason, our preferred way to implement system features is to do all the processing on device. So the question becomes how to positively impact user experience under such constraint. And so that's what this talk is all about. Let's see how we go about it. The first step is to abstract out the different forms of input that are possible. I mentioned some of them already, so like speech and handwriting and so on. And then zero in on the kind of challenges that need to be addressed. Next, I'll touch upon a number of specific solutions that impart input intelligence to a device across multiple applications and look at how it can transform the way we interact with our device. And finally, I'll expand on user privacy in the particular case when it comes to machine learning at scale rather than on device, which is sort of the next frontier in privacy preserving machine learning. All right, so let's get started with the fundamental process that encapsulates user experience. It all begins with the user expressing some sort of need, be it via speech, handwriting, camera, keyboard input, and so on. That's just, the list is not exhaustive. And so this user need can be simple, like, for example, responding to a text message, or complex, like, say, planning an extended vacation with several people. And so once the need is expressed, then comes an intelligence agent consisting of two parts, recognition and interpretation. Recognition takes the input, whatever it was, piece of speech, piece of handwriting, so on, and turns it into things like words, sentences, objects, direct states, and so on. And then interpretation figures out how to best handle the user need given the present context, and handles information exchange with the environment. So this deals with what the intent is, the emotional state of the user, and so on and so forth. Maybe the history of the interaction and things like that. And so overall success in this framework is measured in terms of fulfilling the user need, irrespective of what the form of input may be. And so this leads to an interaction workflow that looks something like this. The input from the user first leads to some sort of semantic interpretation, which can be either complete or incomplete. If some elements are missing, no action can be taken, in which case it is necessary to engage the user so the ambiguity can be lifted. This is the role of interaction management, which relies on the interaction context to figure out what to ask for. So after maybe a few rounds of this, at some point, the semantic interpretation is complete. But then the system still has to pick the best action for the situation at hand. And this is done on the basis of some knowledge about the task and the world in general. And finally, the best outcome is conveyed to the user using the most adequate modality, not necessarily the same as the input modality. So as you can see, this is a pretty complex workflow where every single one of these steps can fail in multiple ways. That means that in order to deploy user-facing features on mobile devices, we have to overcome three different types of challenges all at once: noisy inputs, imperfect AI, and limited computational resources since we're on device. And so the question really is, can we mitigate these conditions in ways that can still benefit the users? And what I'd like to do today is illustrate a number of examples across multiple forms of input where we were able to make a bit of progress in this very challenging situation. And so let's get started with speech input, which is getting more and more widespread these days. We all know about Siri, but not just Siri. We have Alexa, we have Google Assistant, and so on and so forth. And so we can't, of course, cover everything in speech. So I've chosen a very small corner of the problem, just to illustrate some of the most challenging, some of the challenging problems that we face. And that is, I would like to take a closer look at the design of the raise to speak mechanism for hands-free Siri on the Apple Watch. And so that this is a feature by which you don't have to say, "Hey Siri," you just raise your wrist and speak to the watch, and the system will understand that the speech is directed to the watch and then proceed accordingly. So imagine the requirements. This system, this detection system has to be, of course, always on, because you have to be ready to answer a request. So always processing, can't miss a fraction of a second, otherwise the user is not going to be happy. And of course, it has to operate on milliwatts of power, and with a low enough false positive rate. So as I mentioned, the motivation for this work was to create a more natural way to use Siri on the Apple Watch, remove the barrier of having to say the trigger phrase, which in our case is "Hey Siri." But you can imagine the same idea with the trigger phrase Alexa and so on and so forth. But for the user experience to turn out great for all users, there is quite a bit of legwork to be done behind the scene, and so I'd like to take a peek of the sort of the architecture of the system behind this, something that seems to be like a very, very simple feature. And so that's kind of how it looks. The architecture uses a mix of machine learning models of various types. So particularly a couple of convolutional neural networks. A policy model implemented as a state machine, and false trigger mitigation model. The gesture CNN classifies users' motion into 4 different stages: raising the wrist, holding the wrist, dropping the wrist, and then resting, basically other. The speech CNN classifies the raw acoustics into 2 classes: a speech containing class and a non-speech class to reject things that are irrelevant. And of course, the speech CNN has to be trained in such a way that it is only sensitive to proximal speech, because we don't want to react to background conversations and things like that. The state machine decides whether to send a Siri trigger signal on the watch, at which point the piece of audio that contains the user's request is getting processed. And if it's a valid Siri query, then the results will be sent back to the user's watch. So as you can see, a very simple feature like deciding whether or not to accept a piece of audio on a watch requires a tremendous amount of legwork behind the scene. So moving right along, I'd like to now address the next form of input, handwriting. It is of particular interest, actually near and dear to my heart, because Apple's handwriting recognition system was one of the first practical deployment of deep learning on a phone. And that was in the, well, it started in the 2009-2010 timeframe. And the particular context that the problem we're trying to solve is entering handwritten Chinese characters on the iPhone. And we realized that it was a challenge for many users. We had a system at the time that used hidden Markov models, which, I mean, at the time that was kind of the state of the art. But it was not working so well, and for various reasons. It was not working so well for the older population because they were used to cursive writing, as shown in this picture here, which our existing recognizers are at trouble with because it's a difficult problem. And at the same time, the younger population tended to forget the proper writing order for Hanzi characters, for the Chinese characters, which also created problems because, as I mentioned, it was a handwriting, an HMM-based system. So the temporal sequence, the temporal order of things was important. So we had to keep sort of adding prototypes to the system, and it was not sustainable. So we had to develop essentially a new recognition engine, powerful enough to support the full spectrum of users, even non-native writers just attempting to copy a sign, for example, and those people, of course, had no idea of the proper stroke order and so on and so forth. And so the solution was to go full spatial, essentially, use only spatial information, discard the temporal information. And that was not just a problem on the phone, that was also true on the Mac, since the user were able to enter the characters through the trackpad. And so, as you might have guessed, since it was 2010, that was just the beginning of the advent of convolutional neural networks. The ImageNet results had not been published yet, but there was certainly some activities in this field, and so we figured a CNN might be the way to handle this. The problem, of course, was that to scale it in such a way that we could use it on a device, especially that we wanted to support, so as I mentioned, stroke order independent recognition, but we wanted to support something like 30,000 characters, because we wanted to support not just the normal set of characters that are necessary, for example, to read the paper, but also we wanted to support writing names of people and places and so on and so forth. So we figured that takes about 30,000 characters. And so that was quite a challenge to fit it on the phone, especially at the time. Of course, handwriting is not restricted to Chinese. The advent of the iPad Pro and the Apple Pencil has opened up many more opportunities to handle handwritten documents. For example, in Notes, users are now able to search for text through their handwritten notes, such as here for the word equilateral. You see the highlighted, actually handwritten trace, which is very useful to find material. And of course, talking about scaling across platform, the advent of the Apple Watch has opened up the opportunity to bring handwriting support to a much smaller form factor as well, like here with what we call Scribble, to input characters on using the watch. So this necessitated working closely with the hardware side of the company to provide on-device, real-time, battery-preserving performance on the watch. Okay, so that concludes what I wanted to say about handwriting input. Another important modality is camera input. Often a photo is the most convenient way to capture content that would be otherwise cumbersome or impossible to enter in any other way. And so an example of this is going back now a few years, we provided a code recognition solution for iTunes gift card redemption, which was originally intended to make it possible for non-sighted users to redeem their gift card. Because obviously they couldn't really see the characters, so couldn't input them. But like many assistive technologies, it quickly became popular with everybody, because who wants to input a tedious sequence of obscure characters? Much easier to take a photo. And so that worked well, but of course we had control over the format and everything. So in a way, that was a relatively constrained environment, and we could do well. But then we needed to extend this solution to tackle credit card capture for Apple Pay. And that was quite a challenge, because we had to extract the information in real time and with high confidence. And unlike with iTunes gift cards, we had no control over the layout of credit cards. And in fact, I was completely shocked to see the range of design that's available out there, especially when you go international. And that made it quite a challenge to support cards from all over the world. And over the years, we had to develop expertise in very diverse areas, like highly complex foreground background segmentation, various forms of skew correction, rotation invariant recognition, and gracefully coping with low light. And so most recently, we crystallized all that expertise into making a full-fledged text recognition API intended to support a wide variety of use cases, such as from left to right, dense pages, the sort of traditional OCR case, but also different forms of codes, business cards, menus, recipes, various signs and landmarks, building names, receipts, and so on. There is a huge variety of such what we call focused text out there. And because it was the clear intent of the user to save it for later, it is important to make sense of it. So in order to do that, we rely on neural models for both text detection and text recognition components. Let's take a closer look at each of the components, starting with the detector. The input image is fed into a multi-channel fully convolutional network to produce promising candidate regions, most likely to contain text, which are then refined through thresholding and non-maximum suppression. To illustrate, here is the heat map on the right, resulting from the input image on the left. And you can see the in sort of the white areas with the purported image fragments. Now, every image fragment is then fed to a convolutional recurrent neural network, essentially a hierarchy of convolutional and recurrent layers, followed by connectionist temporal classification on top to recognize the underlying sequence of characters. Okay, so this brings us to the last input modality that we haven't covered yet, which is the keyboard. For many of us, this is still the primary form of data entry into a device, so it's particularly important to create an awesome typing experience. The basic idea is for the keyboard to offer predictions for the following word, completions for the current word, and autocorrection for likely typing errors once the word has been committed. So that way the user can stay focused on the ideas they like to express instead of how to input them. What we see here is an example of autocorrection on iOS and the similar form on macOS desktop. Here is an example of auto-completion in English and in Portuguese. And here are examples of prediction and conversion across various languages. We support monolingual predictive typing in about 20 languages and bilingual predictive typing for the most common pairs. I'm sorry, did you have a question? I heard something.
No, sir, I think by mistake someone has unmuted. I think.
Oh, okay, okay. All right, very good. So I'll just, okay, continue then. And notice that we also have transliteration keyboards. I show here Hindi, but we also have now also Marathi and Bangla. And of course, we are progressively adding more and more languages as well, Indic languages. Okay, so to do that, how do we do all these sort of prediction and conversion and so on? Of course, we leverage language models to reduce ambiguity in the input stream, particularly recurrent language models, since we have to model a sequence of words. Here I show an example of an LSTM, but of course we can also use more sophisticated models such as transformers. And so why is it important to model the sequence? That's particularly important to capture long distance dependencies. So in this case, for example, you can see that a trigram would just not cut it. We would not be able to distinguish between, the fact that predictions like dinner, salad, or lunch are much more likely after the verb ate than after the verb found, irrespective of the number of words intervening in the interval. And this is especially critical for languages with sometimes complex syntactic agreements. In Spanish, for example, but in most Romance languages, it is not acceptable to predict the feminine form of the word after the masculine form and vice versa. So buenas after niños would not cut it. One last thing I want to mention regarding keyboard input is continuous swiping, which at Apple we call QuickPath. My group also develops the models that convert swipes into words, as you see here in English, as well as other languages like Chinese. And we do it at the phrase level in Chinese, since the notion of word is not as clear-cut as in English, but it's the same idea. All right. So we've seen various ways to enter text more easily using various modalities. But to input intelligence to your device, you need more than that. That was kind of what we've talked about so far is the recognition part. Now we need to talk about the interpretation part. And that's where natural language processing comes in. This is done through a toolbox of capabilities that are necessary to incorporate NLP, natural language processing, at the user interaction level. Capabilities like part-of-speech tagging and named entity recognition, for example. I'm not going to go through all of that. Suffice to say that these building blocks rely on a combination of linguistics and machine learning, as well as additional services such as word embeddings. And perhaps the easiest way to illustrate how NLP adds value is to look at how it improves the typing experience that we were just talking about before. Here, for example, in this screenshot, we exercise both language identification and tokenization to select the correct range of characters in response to a double click. So you see the yellow highlights there. Which has figured out that the first two characters were sort of a good selection for the intended word. It's also critical in these other areas on the right that we're going to go through one by one to illustrate. So here is an example where we make the typing experience more expressive by suggesting emojis to complement the text as the user types. And again, that's a sort of a very simple feature, but this avoids context switch between regular keyboard and the emoji keyboard, which normally you have to sort of do a little bit of maneuvering to find. So by just suggesting a keyboard on the candidate, suggesting an emoji on the candidate bar, it considerably speeds up the accessing those emojis. And another related feature is how we've recently improved photo search in the Photos app. It is relatively straightforward these days to do scene recognition, but the vocabulary used to describe the scene is necessarily limited to maybe 1,000 words or so. And so in this example, the photo is aligned with the words cloudy and sky, which is fine, but a human might consider the best descriptor of the photo to the left as maybe thunderstorm. And if thunderstorm falls outside the supported lexicon, then no results will be found. So what we've done is leverage word embeddings to, shouldn't have pressed, sorry. Here we go. So what we've done is leverage word embedding to suggest related search words that are supported by photo search, as shown here. And this is a very easy way to improve photo indexing, which in turn offers tangible benefits in terms of enhancing user experience. Another example is how we handle proper names. So in this case here, I can mistype the name of my friend Caroline, and it will autocorrect and complete correctly because Caroline is a relatively common English name, so it happens to be in the lexicon. But that's not the case with my other friend, Devang. And so the keyboard used to fail. The solution was to add a component that proactively identifies Devang as a named entity I care about by just looking at my contacts, for example. And now I can type Devang just as easily as Caroline. This kind of keyboard personalization extends to named entity that I encounter while browsing the web, reading news, or in incoming mails and messages. And so now I can easily get the correct spelling for Skogga, a beautiful place in Iceland, including the diacritic and everything. Another cool feature is to offer proactive responses in specific contexts. The idea is to surface structured data that is cumbersome to type, like the current location, a phone number, an address, or even a specific app. This helps the user stay focused on the message exchange and not lose the context by having to hunt around for information in different apps, for example. On that topic, I'd like to highlight one aspect in particular, which is that we parse questions containing a choice, like in this case, pizza or sushi, and bring the two alternatives to the candidate bar for faster response. This is for messages on both the phone and the watch. The larger point here is that there are multiple ways we can leverage on-device knowledge to benefit the user across various input modalities without necessarily having to solve the full AI problem, which of course is fortuitous because we're very far from having solved the full AI problem. Okay, so that's the good news when it comes to improving interaction experience. But can we do even better? So as I mentioned up to now, what we've talked about, this is all done, the processing is all done on device. But in the last part of the talk, I'd like to revisit user privacy, particularly in the context of machine learning at scale. So we've just seen many features, as I mentioned, that import input intelligence to your device, and these features all work seamlessly with user data in a privacy-preserving manner because, as I mentioned at the beginning of this presentation, for every single feature that we've been talking about, processing is done on device. But that raises an interesting question when it comes to model training. What about machine learning at scale? And indeed, let's take a look at the traditional user scenario, the training scenario. Typically, data is gathered from a bunch of users and sent to a central server. Next, it is aggregated and used to train some machine learning model. And finally, some appropriate outcome is sent back to every device. That's a scenario that unfortunately puts privacy at risk. Because even if we assume that the server is perfectly secure, a bad actor can easily observe private data in transit. And so the question is, does that mean that respecting privacy is the end of machine learning at scale? That would be unfortunate because aggregating data across users is always beneficial. Particularly in terms of model robustness. The more data, the better. So the challenge is how to leverage data at scale while at the same time maintaining privacy. Fortunately, there are a number of possible approaches that can address that challenge. with increasingly stronger levels of privacy guarantees. And let's go now over each of them in order. So the first solution involves pseudonymization, the process of obfuscating personally identifiable information, or PII. Let me illustrate it through an example related to language modeling. So the training of a language model typically involves many different sources of data, of text. And suppose we'd like to add email as another source of data, alongside Wikipedia and whatnot. Then we would need to ingest users' emails, such as this one here. And of course, the problem is that this email contains tons of personally identifiable information, such as names, phone numbers, addresses, and so on. And so what happens in pseudonymization is that the idea is to replace each piece of personally identifiable information with a generic token. So for example, every time we see a phone number, we replace that by a token phone number. And so the picture, the earlier picture gets modified a little bit. We now add an obfuscation block that generates redacted data, a little bit like those declassified documents that come out of the FBI with lots of square black boxes. And then the entire machine learning pipeline becomes generic, and private data can no longer be observed in transit. So problem solved. Well, not quite. If a bad actor is able to observe the database just before and just after a user is removed, such as in this particular case, user 2 is removed, then it can be shown that a lot of private information can be reconstructed from that. Private information about that user too. And so to address that weakness, we have to sort of up our game a bit and look at the second solution, differential privacy. Again, I will illustrate it through an example, this time related to the kind of keyboard personalization that I talked about earlier. Suppose we'd like to learn which emojis are increasing in popularity. And for that, we'd like to find out how many times every user has used a particular emoji, like this one, for example, this surprise emoji or something like that. But of course, we'd like to keep that information private. We don't want to know which users have used which emoji. And so to do that, we're going to add some noise to the emoji count, typically from a Laplace distribution as plotted here. But we could also use a Gaussian. So then every individual emoji count becomes meaningless. In this particular case, it even becomes negative. But because the mean of the noise distribution is 0, we can still gather some useful information about the aggregated count of that emoji across the entire population of users. And so the earlier picture gets modified some more. There is now a differential privacy block that generates crumbled data. So now it's a little bit like those encrypted documents that come out of the CIA, bunch of X numbers or whatever. And then the machine learning pipeline operates on the noisy data. And at the end, we have another differential privacy block that effectively decrypts the outcome. That's way better than before because it comes with strong mathematical bounds on privacy loss. But the problem is not yet completely solved. There is a potential weakness, however. If a bad actor is able to observe the database for an extended period of time, then that actor can track what's happening with a particular user. So in this case, we again chose user 2. You see the database changes, but the bad actor is able to track stuff that's happening with user 2. And then again, it can be shown that a lot of private information can be reconstructed. This can be prevented through what's called the privacy budget, which is essentially the number of samples that any user is allowed to contribute in any given time period. So the sort of limit the amount of information that can be gathered about that particular user. But as you can imagine, there is a trade-off. Because of the privacy budget, differential privacy does not provide the same level of utility in all situations. And so it can become very tricky to balance utility and privacy, as shown in this particular graphic here. And so that brings us to the third solution, private federated learning, to address those cases for which differential privacy has low utility. So once again, I will illustrate it through an example involving language modeling. Suppose we'd like to track across the entire user population how linguistic usage patterns evolve with time. So for example, today, as we've seen earlier, the best prediction after yesterday I ate a really big happens to be salad. But what if in the future we all become even more health conscious than we are now, and the optimal prediction becomes wheatgrass souffle? We'd like to find that out, but of course, without revealing any individual user's information. And so the best way to do that across all possible contexts is to move the learning piece of the pipeline from the server to the device. And now, instead of the data itself, obfuscated or otherwise, we only send gradients to the server, and what gets sent back to the device are parameter updates. So in effect, the model undergoes adaptation directly on the device. And of course, that assumes that enough computing power is available on the device to do that. So you've seen this sort of gradual transition of processing load, sort of moving from the server to the device. And this is kind of the accumulation of that. Okay, so let's recap the various trade-offs associated with the three paths to privacy that we've just covered. In terms of three criteria: privacy, utility, and efficiency. So pseudonymization is practical and efficient, but comes with no privacy guarantee. In contrast, differential privacy does. But as we've seen, in certain situations, its utility is limited by the privacy budget. And finally, federated learning provides the most flexible combination of privacy and utility, but it is computationally more intensive. Now, of course, as devices keep on gaining power, this aspect becomes less and less of an issue. Hence, the third solution, private federated learning, comes across as the most promising avenue going forward. And so we are sort of standardizing at Apple on this method in order to do things like learning new words to add to the lexicon and things of that nature. Okay, so having such path to privacy at our disposal makes it possible to use machine learning at scale in order to not only deliver great features, but to do so in a privacy-preserving manner. So there is no longer an either-or proposition. Instead, privacy becomes just part of the amazing features that the team delivers. And I think that's a profound change in sort of mentality across the industry, but that's slowly seeping through. And again, thanks to GDPR and other regulations like that provided really an incentive for doing that. Okay, and so for a fun illustration, I'll conclude my presentation with a short video called Privacy Matters. And again, I mean, this is an ad for the iPhone, so I apologize for the commercial aspect, but I think it illustrates very well how protective human beings are when it comes to their privacy. So let's take a look.
Let me see.
And that concludes my presentation. Thank you very much for your attention, and I'd be happy to answer any questions if there are any.
Thank you very much, sir. Any questions from the audience? You can unmute
Nice
your mic and you
presentation,
can
sir. Jerome sir, it was very informative. It was very nice.
Thank you.
Can you throw some light on the face input, sir? Face of persons as the input to iPhone?
On the face input, oh, you mean like face recognition, like Face ID?
Yes, sir. Yes, sir.
Yes. What would you like to know about Face ID? In terms of privacy, or?
No, privacy. Yeah, in terms of privacy also, people say that it is not able to distinguish between the twins in iPhone particularly. Maybe the identical
Okay.
twins.
Yes, yes.
I was just curious to know what may be the problem, sir. That's all.
Right. Well, I mean, it's it's a machine learning algorithm. It's a machine learning approach. So obviously, it's not going to be 100% accurate. There will be failure cases.
That is agreeable, but
yes. So
with
we
the
have.
learning, it should have distinguished, no, sir. Otherwise, there is no security involved in that, right? Twins are different characters, yeah.
That is correct. So in terms of privacy, of course, the Face ID resides on the phone. Nothing is ever sent to any server whatsoever. And so therefore, it is secure from that point of view. Now, in terms of failure modes, of course, we are aware of the difficulty of distinguishing, for example, twins. Or other people who are very, very look-alike. And in the particular case of twins, the issue, of course, is that if you look at the general population, the number of twins is rather small compared to everybody else. And so therefore, the training has not seen a lot of cases of twins. And that is part of the problem, since the training data is not comprehensive in terms of coverage of certain similarities, shall we say, then of course we expect that those similarities will be difficult to tease apart. That's an inherent problem in machine learning. So the solution is to keep on training on hard cases, do sort of an active learning approach to gradually improve the performance. And I guess that would be the best answer. I realize that this is not quite satisfactory. Because we, of course, everybody would like a 100% success rate with no false alarm. But unfortunately, that's not quite achievable with the current state of technology.
Yeah, that's a good answer, sir. But my question was like, why I asked this question is, the humans are able to distinguish between the twins, and why computers are not able to do that. That's all my question was.
Yeah, that's a good question. Actually, I will sort of qualify your statement. Sometimes it's very difficult for humans to distinguish between some twins. And what happens is that at the beginning they may not be able to, but they sort of within a few maybe a few times of encountering the twins, they sort of adapt very quickly, and then finally they manage to do it. So they may not be able to do it right away, but somehow they zero in on some distinguishing features, which makes it then later on makes it easy to distinguish. And so I think this solution is really adaptation. We are not going to be able to, I think, off the box, do a very good job of distinguishing between twins. But if we specifically adapt to those the particular case under study, then we'll be able to do it.
Thank you
There is
very much, sir.
another point to that is people say that Apple iPhone is not able to distinguish between the twins only for Asians. Is it true, sir?
Only for
Asians.
Asians? Oh,
Ah.
yeah. I mean, so that's another facet of things. So I'm not going to comment on the particular case of Asian twins, but definitely, I mean, more generally, and not just for Face ID, but generally for machine learning, there has been reports that the accuracy of algorithms vary quite a bit sometimes, depending on and the socio-economic or even racial profiling and so on of the people involved. And that, I think, has to do with the basic composition of training data. I think that very often training data is not properly balanced. So there are more cases of one particular case than others. And so at the beginning, I think people were not quite aware of the importance of sort of limiting bias in the training data. And I think now there's been a lot more efforts to make sure that that this happens. This is all a matter of gaining trust on the algorithms, and this is way beyond just Face ID. This is throughout the sort of artificial intelligence these days.
But knowing the reasons, we should have solved it, no, sir, by this time.
So we can solve it. The way we solve it. So first of all, we have to be aware of it. Like, for example, classic case in language modeling is in a case like a sentence having to do with surgeon and nurse, for example. It's very likely that surgeon will lead to a masculine pronoun later on in the sentence, and nurse will lead to a feminine pronoun, because historically there's been a lot more male surgeons and female nurses than the other way around. So the thing is, first we have to realize that inherent bias that's rampant throughout the training data. And then the way to address this is to perform data augmentation in such a way as to reduce that bias. So every time you see a sentence in the training data with a surgeon leading to a pronoun, a masculine pronoun, then you add the same sentence to the training data, but with a feminine pronoun, and vice versa for nurses and so on. And that works quite well. But as I said, the first step is to become aware that there is in fact a bias in the training data, and which type of bias is there. And then we can address it.
Thank you, sir. Thank you for your comment. Thank you, sir.
Thank you very much, sir. It was a wonderful presentation, and we are very lucky to have you on this distinguished lecture series, sir. It was really wonderful. And it's very amazing to know how much of efforts would have been put to input all the intelligence into the mobile device, and it has made very wonderfully. And all kids, starting from kids to the old age people, are very passionate to have their own personal mobiles, that too smartphones, and all that. It's very amazing, sir. And the journey of you people in the Apple, and everybody is fond of Apple devices these days, is wonderful, sir. Very thank you so much, sir. We would like to have you in future IEEE distinguished lecture series, as well as in workshops, as well as in conferences, as a keynote speaker or expert speaker, sir. Thank you so much for your association with IEEE SPS Bangalore chapter, sir.
Thank you very much. It was a pleasure. It was a pleasure to give this presentation to the Bangalore chapter, and yeah, I hope that our paths will cross again in the future. Thank you.
Definitely, sir. I thank all the participants for your active listening and for asking wonderful questions. Thank you, one and all. Thank you so much.
Thank you, ma'am. Thank you, sir.
Thank you, sir.
Thank you.
Have a good day.
Thank you, sir. Thank you, Nagamani madam.
Thank you, ma'am.